Contingency tables, Chapter 11. Example 1, a random sample of 210 gonorrhea patients is taken from the population of all gonorrhea patients. The patients are randomly assigned to one of three treatments. The treatments and results are summarized in the table below. There were 70 patients that were given penicillin, treated with penicillin. After treatment, 50 had a positive smear, 10 had a negative smear positive culture, and 10 had negative smear negative culture. 70 patients were treated with a low dose of spectinomycin. After treatment, 10 had positive smear, 30 had negative smear positive culture, 30 had negative smear negative culture. 70 patients were treated with high dose of spectinomycin. After treatment, 30 had positive smear, 10 had negative smear positive culture, 30 had negative smear negative culture. With 95% confidence, we want to test H0, response is independent of treatment, versus HA, response depends on treatment. Okay, so these are going to be our observed values here, and we want to compute a similar table of expected values if H0 is true, if response is independent of treatment. So 011 would be the observed in row 1, column 1. So this is the first row here. 012 observed in row 1, column 2, and 013 observed in row 1, column 3, and so forth. So we want to compute a similar table of expected values, so what we want to do here is compute the column totals and the row totals in order to compute the expected values. So, and we want to use those for the expected values. So the total for the first column, 50 plus 10 plus 30 is 90. Total for the second column, 10 plus 30 plus 10 is 50. Total for the third column, 10 plus 30 plus 30 is 70. And the row totals are all 70 each. The grand total is 210. Okay, so we're going to use those same totals here for the expected values. So I'm putting the same column totals and row totals from the observed chart, and then to get the expected values, we want to multiply the column total times the row total divided by the grand total. So this maybe kind of reminds you of what we're doing with probability if they were independent. When we're using a box to create probabilities, if they're independent, we can multiply the row column times the row to get what's inside the box. So this is sort of the same idea here. So for expected in row 1, column 1, it's 90 times 70, that's column 1, total is 90, times the row 1 total is 70 divided by 210, the grand total, and that comes out to be 30. And each of these in the first column are all going to be 30 because the row totals are all 70 and the column total is 90. So the first column they're all going to be 30. The second column, the column total is 50, the row total is 70. 50 times 70 divided by the grand total of 210 is 16.6 and repeating sixes. And that, again, that's the same for each of these because these row totals are all the same and the column total is the same. And then the third column, we have 70 times 70 divided by 210 comes out to be 23.3 and repeating threes. Again, that's the same for all these because this third column all has the same row total and the same column total. In a different contingency table, it might be that these row totals were different, but it's common when you're testing different treatments and divide the patients into treatment groups. It would be common to have all the treatment groups be the same number of patients, but it doesn't have to be that way. They could be different numbers of patients. Okay, so these are our expected values if H0 is true, and then we want to check that none of the expected values are less than 1, and that's true, that none of them are less than 1, and no more than 1 out of every 5 are less than 5, and in fact none of them are less than 5. All of our expected values are at least 5. If our expected values were too low, we could maybe combine some of the rows or something to so the expected values were not so low. But in order to use the chi-square table for the probabilities, we want to those probabilities are only going to be accurate if our expected values are at least all of them are at least 1, and most of them are at least 5. Okay, so then since these were all since these all met the standard, we can then compute our test statistic, and it's going to be observed in the first row, first column, minus expected in the first row, first column, square that, divide by the expected, and so forth. Do that for each row and each column. So we plug in the numbers, 50 minus 30, square that, and divide by 30. 10 minus 16.6, repeating 6s, square that, divide by 16.6, repeating 6s, and so forth. And we get these numbers here, add them up, we get a test statistic of 54 point something. And then we can compare that to the number from the table. So in order to find out which number from the table we need to use, we want to compute r minus 1 times c minus 1. R is 3 rows, C is 3 columns. Our original table had 3 rows and 3 columns. R minus 1 times C minus 1 is going to be 3 minus 1 times 3 minus 1. 3 minus 1 is 2, that's 2 times 2 is 4. So we want to look in row 4 in column 0.05 of the chi-square table. And that gives us a value of 9.488. Let me just double check the table here. Yeah, that's our chi-square value here. That's in might be a little hard to read. Row 4 and go across the column 0.05, and it's 9.488. Okay. Okay, so our test statistic is 54 point something. It's bigger than the upper critical value that we got from the table, 9 point something. So that means we reject H0 with 95% confidence and conclude that the response depends on treatment. And that concludes this presentation.